7 isn't due until after spring break.
Essentially, yes.
Okay.
Yeah. Okay. But with problems at 8 on horizon, it's still a good idea to make progress on it this week. Okay, one general comment I want to make about the set I just handed back. So when we have a problem like this, well, actually now I think about it, a couple comments. Beware of a case where one of these coefficients is 0. I brought this up before, but a few people fell into this trap. One of the textbook problems had this situation happen. If you have something like y double prime plus constant py prime is equal to 0, so there's no q term, your characteristic equation is r squared plus pr is 0. But if it's the other situation, where qy is equal to 0, your characteristic equation is r squared plus q is equal to 0. So when you only have two terms, and one of them is going to be y double primes because we're doing a second order equations, but pay close attention to whether the other term is a y prime or a y. It's a common mistake to put an r in that second term where it shouldn't be, or vice versa. So that's one stumbling block for some people. And then separate thing, try to pose initial conditions. Say y is 0 is y naught, y prime is 0 is z naught, and let's suppose your general solution after you find the roots of your characteristic equation, and you have that, and then you go to satisfy the initial conditions. Now, in this case, when the initial time is 0, we have to solve this system. C1 plus C2 is y naught, and let C1 plus lambda 2 C2 equals z naught. But can someone tell me, why is that the equation to solve? Like, why this one? Where does it come from?
Because if you plugged in 0 for the t, your e would go to 1.
Yeah, either 0 equals 1. This is important, though, the initial time. So if initial time is not 0, so another way to think about it is, if I were to generalize the initial conditions, y t naught is y naught, y prime of t naught is z naught, then the equation you're solving is c1 e to the t lambda 1 t naught, or whatever it is, plus c2 e to the lambda 2 t naught is y naught, and then a similar equation for the derivative. One is, just like initial conditions that we solved back in the last chapter, where it was first order equation, so we only had one initial condition, you're always plugging in the initial time, setting it equal to the initial value. That always works. If you're going to, while it can be helpful to remember things like this as shortcuts, remember these things halfway ends up setting yourself up for trouble. It's important to also retain an understanding of why this is, when this is, under what assumptions is this the case. So remember the technique itself plus the context. That's why I do see memorization of certain things as a helpful convenience, especially for tests. Without that bedrock of understanding where all things you're memorizing come from, it can come back to haunt you. So it's important to find that balance there. Okay, now continuing with other situations for second order equations, because we're about to get to the last situation, repeated roots. But first, recap of what I covered at the end of last time. Reduction of order. So this is for more general second order equations, where even variable coefficients are possible. Okay. So you're given a solution y1 of t, and the problem is what is the second, and I want to emphasize here, linearly independent solution. So this is of interest in a case where you solve your characteristic equation, you get a double root lambda, so you know e to lambda t is a solution, but you need a second solution to describe all solutions. And in that repeated root case, we still don't know what that is yet. So what I arrived at last time, just to summarize, is so we call the second solution y2 of t. We have a formula for it now. So y2 of t is equal to your first solution, y1 times some function v of t, where v prime of t is equal to 1 over y1 squared times e to the minus integral of p of t. So this is what you need for, so this is called reduction of order. So reducing this equation to a first order equation is how this was obtained last time. So reduction of order produces this result. So now I'm going to show how you would use this to find a second solution for an equation given a first solution. And then we would use it for the case we're really interested in, and that is handling the case where the characteristic equation has repeated roots. Well, so one, and actually it's also confirmed in the notes that once you get y2 and y1 really are independent. Their Wronskian can be shown to be non-zero, so you don't have to, so you know you can use y1 and y2 to describe your general solution. Okay, so an equation like this where p and q can depend on t, we don't have formulas for solving in that case. For certain cases, we know a solution. So it's unfortunate that I really can't address those generally. In fact, trying to address those more generally is one of my research topics. But at least in this case, I can give you a solution so that you can use reduction of order to find a second one. So here's our equation. Now, make sure the equation that you're given fits the form for which the technique out here applies. Again, context. Here it's assumed that y double prime is by itself in order to determine what are the coefficients p and q. So we need to do that here. We need to divide by t squared to isolate y double prime. So we have y double prime minus 4 over t y prime plus 6 over t squared y is 0. So this gives us our p of t. And not that we need it for this example, but this is our q of t. So you can just take it for granted, or you can confirm it yourself if you like. A solution of this equation, or y1, is t squared. So the question now is, what is y2? So now we can go ahead and use this formula over here. So first we get v prime. So that's going to be 1 over y1. So that's 1 over y1 squared. So it's 1 over t squared. And then e to the minus integral of p of t, which is, watch your signs, minus 4 over t dt. So this is just from plugging in all the pieces of a formula over there. So any questions at this point before we actually work that out? All right. Now, the integral. What's the integral work out to be? Yeah, so a 4 as constant, then we just have 1 over t, so e to the 4 natural log of t. Now this, what does that simplify to? The whole thing simplifies to 1, but what I circle?
T to the fourth.
T to the 4th. Because this is, the exponent moves up here, so this is the same as e to the ln t to the 4th. The e to the ln cancel each other out because they're inverse functions of one another. That is t to the 4th. So we get t to the 4th over t to the 4th. So yes, our v prime of t is equal to 1. All right. So now we finish it off. y2 prime is equal to y1 times v. Well, y1 is just as t squared that we given earlier, and then we just integrate the v prime from a previous step. In this case, there's no need for a constant of integration because you're just adding on a multiple of y1, and you already know that y1 is a solution, so it's redundant.
That is y prime, right?
Um,
Up top, 4 over t, y prime.
Yes, that is, yeah. Okay. Good catch. So what's our final result?
T cubed.
Yeah, t cubed. Okay, so now what we can say is the general solution of this particular equation has this form. Y of t is a constant times t squared plus another constant times t cubed. Now sometimes when you apply reduction of order, you might get your y2 to be some function times a constant. Any constant factor is actually irrelevant if it had come up. Like suppose this had been t, so we'd get t squared over 2, so t to the 4th over 2. Because what happens in general solution, it gets multiplied by a constant anyway. So that's a optional thing when it comes to writing down answers. What we're looking for is what type of function is it? Is it a power of t? If so, what power? Is it an exponential? Is it a sine, cosine? Things like that. Whatever is minimally necessary to describe all possible solutions. Okay. So any questions about how reduction of order works to get y2 from y1? Okay. So can you be prime from this formula that was worked out last time? 1 over y squared integral of minus p, or e to the integral minus p, and then your y2 is assumed to have this form. Okay. Now, finally, oh, blue chalk, that's fantastic. And, there is another eraser. By the way, how did, those of you to whom this applies, how did that probability determined go last night?
The what?
Probability?
Oh, it's horrible.
Sorry to hear that. Now, I saw so many of you here. I have my graduate class here. Yeah, I sense the misery. Okay.
Not bad.
You'll have Dr. Harris.
Yeah.
Been there.
Well, hopefully Dr. Harris shows some mercy.
He's usually pretty good at questions, so I'm just saying.
Okay, let's see if this works.
works any better.
Okay, so now we look at repeated roots. So back to our case of constant coefficients. So you go ahead and solve your characteristic equation, r squared plus pr plus q is equal to 0. And if you just go ahead and apply your quadratic formula, so r is minus p plus or minus square root of p squared minus 4q over 2. And we're interested in the case where this discriminant ends up being equal to 0. So we've already covered cases where it's strictly positive and strictly negative before. So we get minus p over 2 both times. So now you think, okay, your solutions y1 and y2 would normally be e to the minus p over pt over 2 and then e to the minus pt over 2 again. Those don't describe all the solutions. So we have our one solution. Y1 of t is e to the minus pt over 2. And I'm going to also write this as e to the lambda t, where lambda happens to be minus p over 2. But knowing what it is specifically is going to help us to work out what the...
What do you mean p over 2 twice?
in other words, it's normally a plus or minus because of quadratic formula.
Yeah.
But you end up just having the same value both times. Yeah. So yeah, that's a repeated root case. Okay. So what we do is we use reduction of order to find y2 of t, just like in the previous example. So follow the same steps. So we have v prime of t is 1 over y1 squared e to the minus integral of p dt, where p is now, in this case, happens to be a constant. So we fill in what y1 is. It's e to the minus pt over 2. Squared, and then we have e to the minus pt after evaluating the integral. So what happens when I perform the squaring here? What am I going to get? Yeah, despite laws of exponents, the exponent of squaring, the exponents multiply. So I have e to the minus pt up top, and now I also have e to the minus pt down below. So our v prime turns out to be 1. Now, what's kind of unfortunate is, for this example and the last example, through highly invalid extrapolation, one might think, oh, v prime is always 1. Trust me, it won't be on the test. So.
Can you explain what you did again with the squaring?
Oh, you multiply the exponents.
Uh-huh.
So then it gets, let's get e to the minus pt. Yeah, because the 2's end up canceling. All right. So now, following the second step, y2 of t is y1 of t v of t. But if we fill in what both of those things are, we have y1 is e to the lambda t, where lambda is our root, and then the integral of v prime. So we just multiply by t. So you get t e to the lambda t. So that's what happens in a repeated root case. You have the exponential solution that you normally get from a case of distinct real roots. That's your y1. And then you just multiply that by t to get the second solution. All right. Is there any questions about how that was obtained? But now when you have a repeat, if you are given a problem like this and you don't know what the roots are going to be, it could be any of the cases, real distinct roots, complex roots, repeated real roots. You go ahead and solve this, you get your two roots, and if you find that you get the same root in both cases because your discriminant is 0, another way of putting it is your characteristic equation happened to be a perfect square. When that happens, there's your y1, and then you can jump directly to doing this y2. You don't go through this again. You just use the fact that in the repeated root case, this is part of your general solution. So now I'll illustrate that by stepping through a repeated root example. Okay. So we have this initial value problem. So y double prime minus 6y prime plus 9y, 0, and then these initial conditions. Okay, very generic looking initial conditions. Okay, so you do like rubber problems. You find a characteristic equation. So you have r squared minus 6r plus 9 is 0. So what happens when you factor that? What?
R minus 3 squared.
Yeah. R minus 3, R minus 3. So you get repeated roots. So your roots is, so 3 is your only root, and therefore it is a double root. So your general solution is a constant e to the 3t, like you normally get for real roots, plus c2t e to the 3t. So once you solve a characteristic equation, you find this is what happens, it's a perfect square, just jump directly to this. I've seen it happen on homework or especially tests where you get repeated roots and then you just go ahead and write down this and you forget the t. Well, then all you have is a constant times e to the lambda t that doesn't describe all possible solutions. You end up not being able to solve these equations to satisfy your initial conditions. So now we look at satisfying the initial conditions. And in the case that we often, but not always have, where initial time is 0, things work out pretty conveniently. So y of 0, what happens when I plug in t equals 0 into that? Just C1, because you have this factor of t here. Similar thing happened in a complex case. So now, that's supposed to be 1. So C1 is handled immediately. What about y prime is 0? So we're going to have 3C1 for your first term, but what do you have to do in the second term? Yeah, unfortunately you have to use a product rule. Okay, so we're going to have C2. What is the, we won't plug in t equals 0 yet, but what is the derivative of that? Yeah. But then, I'm going to make a notation here that this, you have to now plug in t equals 0, but then things still work out pretty nicely because at least that term is going to go away. So what you end up with is 3c1 plus, this becomes 1, so c2, and that is equal to your y prime value, that is 2. So,
What happened to the e to the 3t for the c1?
Well, we're plugging in t equals 0.
Oh,
That's why we're only left with C1. Okay, so what is C2? Yeah. All right, because C1 is 1, we can plug that in here and solve for C2. Okay, so your solution is e to the 3t minus t e to the 3t. So that solves the ODE and satisfies the initial conditions. So what we can say in general, based on this, extrapolating a little bit, if you have your initial conditions specified at t equals 0, your equations, well, C1 just turns out to be y naught. So that's not very interesting. And then for your second equation, it always turns out to be lambda C1 plus C2 is equal to Z naught. So C2 turns out to be Z naught minus lambda Y naught. If initial time is non-zero, then you're going to have some exponentials in there with the initial time plugged into them, so it's a little messier. Solving a system of two equations, two unknowns. Okay. All right, so any questions about repeated root case? So now we've covered all the possibilities. When it comes to these second order linear equations of constant coefficients, you're always solving your Kesher equation, you're getting your roots. And now, whatever situations come up, distinct real roots, complex roots, repeated real roots, we have a form for the general solution. So I'm going to for anyone watching at home, I'm not entirely sure that the whole board was captured in my last example. I can't really tell in my tiny window, so there it is for C1 and C2. Okay. Now, okay. So if I was watching at home, here's what you missed. Pause and read. Okay, I guess I better keep a closer eye on this dang thing. Okay, so complex case, you have real imaginary parts. Okay, so continue the general solution.
what one?
E to the what? Yeah, e to the alpha t times cosine of what? Beta t. All right. And then what's the difference in the other term?
It'd be sine beta.
Sine. Yeah. Remember my hearing is awful. Okay. Okay. All right. So you have exponentials times sine or cosine. So if you have purely imaginary roots, that'll be a case of interest later. You're only going to have, you won't have exponentials because alpha will be 0 in that case. So you'll only have cosines and sines. Okay, and finally, we just saw today, R1 equals R2, and that is necessarily real because anytime you have complex roots, with an actual imaginary part, they're going to be conjugates of each other. So then your solution is constant e to the, so in that case, I'm just going to call it R, since they're the same. So for one distinct root you have, C1 e to the RT plus C2 t e to the RT. And finally, if there's no initial conditions given, you stop there. And then, if there are initial conditions, you substitute T naught, whatever that is, into y of t and y prime of t. And you set those two, so y of t naught, y prime of t naught, equal to the given initial values, y naught and z naught. That gives you a system of two linear equations and two unknowns, C1 and C2. Go ahead and do the elimination and substitution necessary to solve for them. And that's it. You've solved your initial value problem.
Could you explain right there? It's a substitute T naught, then you have equals all.
Oh, that's from a previous slide.
Oh, that was pretty.
Okay. All right. Now, I can assure you that on the test, you'll see all three of these. You'll see all three of these situations. You just won't know which is which until you actually go ahead and solve the character's equation, assuming you don't make a mistake there, and you can proceed as needed for whichever situation it is. Okay. So now we have, in all three cases, a y1 and y2 that are linearly independent. They describe fundamental set solutions. If you were to compute Wronskian, it would be non-zero, at least at most points. So any questions about this procedure? All right. All right, not a lot of time left, but what I will do is to set the stage for Friday. Non-homogeneous equations. So we're going to look at the same kind of equation as before, except we're going to have something non-zero on the right-hand side. Some function g of t. Still same kind of initial conditions. So I want to describe at least the general form of a solution as a starting point for how you proceed on such problems. So the solution, y of t, of this IVP, initial value problem, has this form. So you break it down into two terms. Y sub h of t plus yp of t, where yh is basically what you've been doing before. So that is a solution of a homogeneous version of this equation. So you just set the right-hand side equal to 0 again. Okay. So everything you used before to find a general solution, you're still going to go ahead and do that. That's like one of the free forms that you have over there if the coefficients are constant. And then yp of t is called a particular solution of the non-homogeneous version. And that's what we're going to start covering on Friday, and then this will spill over into after spring break. There's a couple different approaches that we'll see. Unfortunately, they're both going to be a pain. It just depends on what your GT is, but we'll start digging into that on Friday. There's decent notation that I've introduced before when I was talking about the Wronskian at much greater length than I ever intended. This can be written as Ly is equal to G. You've seen this notation before where L is a second order differential operator. So this is L of Y up here. And because it's a linear differential operator, L of Y is equal to, broken down into two terms, YH plus YP, the particular solution. And because it's linear, the operator applied to this sum is the same as the sum of applying the operator to the two pieces individually. But YH is a solution of the homogeneous equation. So that is equal to 0. And then YP is a particular solution of Ly is equal to G, so that is going to be G. So that's why we refer to this as the general solution. Just like before, it's whatever describes all possible solutions of the differential equation. And what's going to happen is YH is, like before, going to have arbitrary constants C1 and C2 in it. It's going to be one of the forms that you had before when P and Q are constant. And these had to be chosen as before to satisfy the initial conditions. But I want to emphasize, in this process, you must include a particular solution. So you're not just going to plug in your initial time, T0, into just the homogeneous part. You're going to plug it into this too, and get a system of equations to solve for C1 and C2. So there's going to be an extra term in each equation. Okay. So the hard part of this is finding YP. So depending on what form G has, is it a polynomial, is it an exponential, is it kind of a combination of sine and cosines? There are different ways to proceed to figure out what YP is. Before and after that, it's fairly straightforward. From there, we just add on this solution of arbitrary constants, and then we see what it takes to find the initial conditions. And during the 2 minutes I have left, I would try to make up an example. Let's suppose we have y double prime plus, say, 4y is equal to t. Actually, take t squared. So then, our particular solution is, and for reasons that would come clear on Friday or after spring break, it's going to have this form is equal to some constant, which I'll call A0, plus another constant A1t, plus another constant A2. So because the right side is a second degree polynomial of t, quadratic, your particular solution is also a quadratic. You substitute that into here, and a second derivative of that would just be 2a2, that's yp double prime, and then plus 4 times all of this. And that must equal t squared. So what you do is you play a matching game. You combine like terms. So what we have is the quadratic term, 4a2t squared is equal to t squared. And then we have a linear term, 4a1t must equal 0. And then your constant term, you have 2a2 plus 4a0 must also equal 0. So now you have three equations that you can solve for a0, a1, and a2. So a1 is certainly 0, and then a2 must be 1/4, and then a0 has to be minus 1/2. Assuming I didn't make a dumb mistake on the fly, because I know I'm out of time. So your particular solution turns out to be minus 1/2 plus 1/4 t squared. That satisfies this non-homogeneous differential equation. So how do you handle this for other g of t's? There's much more to it than that, but this gives you an idea, and we'll start exploring that on Friday.
Okay, that says 4a0 what? 2a2 plus
4 equals 0.
equals 0.
Yeah. Okay, you've all left, but I've just realized that I messed up here. I substituted the wrong thing. So what we have here, I'll fix the video, is in the third equation, 1/2 plus 4a0 is equal to 0. So 4a0 is equal to minus 1/2. So a0 is equal to minus 1/8. So the particular solution is minus 1/8 plus 1/4 t squared. I substituted a2 into this 5a2 into a0 in the third equation by mistake, so that's why I messed up. And just to confirm that, y double prime is 1/2, just plain old 1/2. 4y is equal to minus 1/2 plus t squared, so y double prime plus 4y. 1/2 minus 1/2 cancel, and you get t squared. Okay, so at least you can see the corrected version on YouTube.